Good afternoon. And everyone's eating. Good afternoon. That's better. Thank you, Peter, for that warm introduction. And on behalf of RTX, really appreciate the opportunity to speak with you this afternoon. I'm going to talk about a couple of things, and I want to set the stage for some topics for consideration. And I'm going to walk through some technologies that illuminate some of these topics and sort of paint a picture, starting with the face of warfare is changing. We'll dig into what that means in terms of integrated battle space and connected battle space. We'll also focus on dual use is dual advantage. That's really important, that the ability to make things in the fleet, in the both for our defense as well as commercial. The laws of physics don't change. We optimize those systems to meet the mission, and that industrial base gives us a really important advantage as we look at some of the challenges, particularly that Dr. Erickson outlined for us. I'll also, for OPSEC reasons, give you a lot of commercial examples that also lend themselves towards military applications, but obviously won't share some of the details of those. I'll focus on technology investments and their importance in terms of criticality. Some of these technologies are going to be unlocks, not just let's make more of the same things the other guy's making, but introducing fundamentally new capabilities. And Admiral Small referred to one in terms of additive manufacturing. I'll show you some real-world examples where we're actively applying this and fielding some of these capabilities. And then I'll touch on the role of digital and AI. I'll go into a couple of examples. It's important to, that we embrace digital, especially to go faster. AI gives us some really important opportunities, but these tools really need to be used intelligently and applied appropriately. And that is something I think we're all learning how best to achieve. A little bit about RTX. We are now one of the largest aerospace defense companies in the world, with 185,000 employees, 80 billion in sales, and we invest in technology, our money and our customers' money, about $7.5 billion a year. And I'll show you some of the vectors of those investments. We are deeply penetrated in terms of both military and commercial aerospace. Every second of every day, an aircraft takes off with our content on board. And we control about 2/3 of the world's air traffic. Of those 185,000 employees, we have 57,000 engineers. Those 57,000 engineers have authored over 60,000 patents. We currently hold the record for the largest number of active patents held. And I'll share a little bit about the engagements of the universities with national laboratories, because those are also of critical importance. For those of you who are not familiar, RTX was formed through a merger with Raytheon and the legacy United Technologies aerospace divisions. We brought them together in 2020, April of 2020, and there are three major divisions. Each is really the leader in their particular market. Collins Aerospace makes all of the subsystems on aircraft, from the mission systems, from the avionics, all the way through the electrical systems, the landing gear, the seats that we sit on, the galley systems, the bathrooms, everything, even the emergency slides. That's what we produce at Collins Aerospace. And there is huge opportunity to integrate those across the aircraft platform. Pratt & Whitney is celebrating its 100th anniversary this year, where we make propulsion systems. And that's all we make at Pratt & Whitney. I've personally spent more than 20 years of my career at Pratt & Whitney, and I'll share some of the the types of products, but essentially we're on everything from expendable platforms, missiles, all the way up through business jets, turboprops, helicopters, commercial airplanes, as well as powering significant platforms in the United States military and Air Force fleets, most notably the F-35 aircraft, the F-22 aircraft, the B-21 bomber, the C-17, the KC-46 tanker, just to name a few of the principal propulsion systems that we field. And Raytheon is certainly well known to this community. Raytheon producing missiles, radars, radios, and effectors that really are defending our freedom all over the world today. You can't go a day without opening the news and reading about some of the subsystems and systems that Raytheon is fielding in the fight today. We have a number of firsts from the company. This is on the upper left-hand side, upper right-hand side, sorry, is the SR-71 aircraft that really was a dramatic player to ending the Cold War. Its speed records have not officially been broken to date. Constant cruise at Mach 3.5. First tactical ballistic intercept. Hitting a bullet with a bullet is really hard. And pulling that off and doing that reliably time and time and time again is critical to protect the populations of our allies and through the Golden Dome, our nation as well. In 2015, we introduced a new technology called the geared turbofan. It was a big departure in a re-architecting of commercial aircraft engines, which resulted in about a 16% efficiency gain. And really, it's really transformed. First of all, it led to the disruption of all modern commercial airplanes being re-engined, not all by us, but it really opened up a paradigm shift in the market. It also opened up the fact that now you can travel, say, from the East Coast of the United States to Europe on a single-aisle airplane, and so it's starting to already significantly adjust the demographics of the 30,000 airplanes in the commercial fleet. On the bottom, you see the engine, the F-119 engine for the F-22 was the first fifth-generation fighter engine, capable of supercruise, flying supersonically without engaging the afterburner. That's significant both for survivability, but more importantly for range as well. The first gallium nitride airborne radar, and I'll show you a little more about that as we go forward. But these new sensor systems and material systems are enabling even greater reach. And the first global aviation connection database communication system that really enabled the ability to connect commercial aerospace around the world. So I'm going to talk a little bit through a few themes here. First, the changing face of warfare in terms of the integrated battle space, and then the effects on the industrial base. The battle space has become multi-domain. The singular force structure working without collaboration, without full domain capability is at a disadvantage. And we'll talk a little bit more about what it takes to bring those together. But it's important to note that everything from the air, space, cyber, all need to be working in concert. Persistence. You can't hide. In around 2000, we had about 500 or 600 active satellites. In 2013, we broke the record. We had 1,000 active satellites. Today, there are more than 10,000 active satellites. And by shortly after the turn of the decade, we'll have something on the order of 100,000 active satellites on orbit. And so the notion of persistence is critical, and so it really changes the way we harness that data, but also the way that ops can be conducted. Sensor fusion. Having all those satellites is great, but making sense of it and getting an understanding of what's going on in the battle space is absolutely critical. And that's a critical role for AI, because the vast amounts of data are just so profound. It's really a challenge to interpret that and assimilate the information and turn it into action. Part of that is turning the kill chain into a kill web that we saw in the most recent battle between India and Pakistan, that was a critical ability to be able to use sensor systems on one platform to be able to complete the loop and guide those missiles terminally to their targets, as an example. And of course, that was a Chinese system that was being used by Pakistan at the time. Short response times. I mentioned hypersonics here, but it's not just hypersonics. We've seen some very recent example in the Ukraine with the spider web, and more recently in Iran with some of the exploits of the Israelis in terms of pre-positioning assets, either loitering munitions or hidden munitions that can emerge upon command. And some of those actually emerge on command through commercial networks. And so the commercial networks can be a critical factor. High-low mix of effectors, we'll talk about that a little bit in terms of potential to overwhelm defenses, but the bottom line is the bottom line, that you can't keep shooting down missiles and drones that are relatively inexpensive with exquisite effectors that changes the way the strategy is orchestrated. And autonomy. A couple of years back, Secretary of Defense Hagel talked about offsets. The first offset was really during World War II, where it took multiple aircraft, for example, to take out a single target. The second offset was introduction of stealth and precision munitions. So you could actually have a single aircraft or a single asset take out multiple targets. And today we're seeing the emergence, and it's really evolving real time on the battlefield with autonomy, where a single combatant can command multiple assets over and over again. And so that's really an important, dramatic change that's happening in the space. On the industrial base side, for the first time since World War II, we're in a situation where we went from demand-constrained capacity to supply-constrained capacity. And really, this transformation happened in 2020. We had COVID. Commercial aerospace came crashing down. As we came, and then, of course, the world got to be a lot more dangerous with a number of conflicts emerging. And so when you look at what's happened since, the demand, there's all this pent-up demand for travel. There is a backlog for commercial airplanes. If you order an airplane today, an A320 or 737, you're going to take delivery in the middle of next decade. And so the manufacturing base for those commercial assets, the castings and the forgings, are very much the same as we use on the military side. And then, of course, we have the buildup in China. We have the flooding of weapons into the Ukraine. And so with all of that, there's just not enough capacity on the face of the planet. Public information, RTX, we have a $250 billion backlog of stuff that if we can only make it, we could deliver it. Contested logistics, that's an important factor. In a lot of these fights, what you have available in the region is what you're going to have to do the fight. And in some cases, it could end up being protracted, but in other cases, like Indo-PACOM, probably it's going to be over relatively quickly, at least in some of the scenarios. Magazine depth obviously factors into that. Affordable mass, I mean, that's a critical. I'm going to show you some examples of some technology unlocks for affordable mass. And so supply chain dynamics, this is actually a great application of AI today, that as we look at the supply chain, it turns out that as you start to analyze, we at RTX have about 13,000 suppliers. But there's a couple of really critical suppliers out there that need to keep an eye on that. In Malcolm Gladwell's book, The Bomber Mafia, he does a great example of explaining this in terms of the ball bearings. There's just a couple of things like seekers and solid propellants are currently bottlenecks across the industry. So a little bit about the integrated battle space. First and foremost, particularly in Indo-PACOM, the notion of air superiority and freedom to operate is gone. And with some of these, we see in the seascape as well, with some of the deployment of autonomy, that's likely a similar type scenario. So the fact that there will the fact that we will always have highly contested environments is a reality, and we're going to have to live with that. We're going to have to fight in that domain. There's also the contested domains, and of course the permissive, and it goes beyond just the functions, the command and control, the communications. Precision, navigation, and timing, and I'll say a little more about this, remains sort of a key unlock for some of this multi-domain activities. And then the role of, I guess on the side, you'll see sensors and effectors. Sensors and effectors, again, they're ubiquitous, they're pervasive, and they may not launch from where you thought they were going to launch from. I also highlight here the commercial layer. The commercial space layer, the use of SpaceX by the Ukraine assets is a good example of that. The use also in terms of the Spiderweb campaign as another example. They used commercial telecom networks. So the space layer and the commercial infrastructure actually can play a role if used properly, but it's something we also need to be extremely cognizant of because we're not the only ones thinking of this. In terms of multi-domain connectivity, the real key right now to unlock this is precision, navigation, and timing. The ability to have spoof-proof abilities to understand, essentially using GPS or its equivalent, where you are and coordinating time bases across large domains of different heterogeneous assets, some at the bottom of the sea and some on orbit. That is going to be absolutely critical. And today we're faced with, some of the newer platforms have modular open systems. The older legacy platforms do not. There's limited compute power on board some of the legacy systems that we haven't, quite honestly, manufactured in a long time as a nation. The standards, there's lots of different standards out there, and they're all using different protocols a little bit. And so harmonizing that and bridging across that is actually a really important challenge. And that's sort of a must-do that needs to go be addressed quickly. And it's going to take collaboration across the industrial base, Department of Defense, as well as the administration. And recent events, this is a picture over Tel Aviv from June. Iran launched 591 projectiles, multimodal projectiles, drones, missiles, et cetera. And almost all of it, 90%, was stopped. And in many cases, the ones that were let through deliberately because they needed to conserve the magazine depth not knowing just how much more was on its way. And so that's significant, but again, the notion that if your effector that you're using to take out the projectile is more costly than what's being sent to your shores, then in a war of attrition, that cannot be sustained. So I mentioned a few things. I'm going to talk a little bit more about technologies here. Two things I want to highlight on this chart. We have two research centers. One is in East Hartford, Connecticut, RTX Research Center, which is actually I spent the first 14 years of my career there a very, very long time ago. And then the other one is BBN. We do more sort of hard stuff, experimental work for the most part in the RTRC. And BBN is really more on the soft side, the cyber side, the quantum side, et cetera. We also have, important to note, 10 technology roadmaps, and I'll drill into those a little bit. But we also have, of the 57,000 engineers, there's 1,500 fellows. And one of the things that we recognized is that there needed to be the ability to have people grow in their career to the very highest capabilities, to the very highest comp levels, really, in the organization, while not having people, not having direct reports, may not actually have budgets, but actually to focus on technical excellence. And that is a key to success. Now, I'll highlight the picture in the background here. This is actually a great example. It's the mid-infrared sensor from the James Webb Telescope. We produced this sensor. Why am I showing you a telescope? Well, we make similar systems that look the other way. They look down. Obviously, I can't show you those. And so suffices to say, we can count the stitches on a baseball from orbit. I mentioned these 10 technology roadmaps. A couple of them are very focused on the obvious players, intelligent aviation, advanced propulsion. I'll share with you a little bit from the advanced propulsion technologies. Integrated power and thermal management. This is becoming of critical importance. Another great example of dual use, we see on the commercial side, hybridization of aircraft is starting to be a thing, and you've probably seen some announcements from our company on that. It turns out that there's a sweet spot in the market for around 0.5 megawatt to 1 megawatt that's enabling for low-range payload, and we're starting to see some of these applications on the defense side as well. But it's also being integrated into larger engines as a very mild hybrid. A320 roaring down the runway is 30,000 pounds of thrust, similar to an F-135 engine on the F-35 is 40,000 pounds of thrust. So it's a similar construct. If I had 0.5 megawatt to 1 megawatt on board some of our defense platforms, it might change the way we use power. And we're going to need that between the EW and the DEW systems that we're going to be looking at as we look to the future. Integrated battle space, sensing systems, autonomy is a critical technology, as I mentioned. Microelectronics, we talked a little bit about that earlier. Digital life cycle, and I'll share a little bit about that. AI and how it could be used, and advanced materials in manufacturing. And I'm going to build on some of what Admiral Small said about additive as well. Just some good examples, and again, borrowing from the commercial space, the brakes on the commercial airplanes today have to go to extremely high temperatures. And so these are material systems that are ceramic matrix composites, very high temperature material systems. It turns out that the temperatures you need to achieve to either be on the outside of a maneuvering hypersonic vehicle or on the inside of a jet engine without having to cool the structure, those are the same material systems. And so those CMCs capable of order 2,500 degrees Fahrenheit without external cooling are now being inserted into jet engines, and they're being applied to some of these hypersonic effectors as well. Another example is the advanced radars, gallium nitride in particular. It's been applied across a number of applications for Raytheon defensive radars. We're now starting to apply that on the commercial side. And so that drives down cost, it increases manufacturing base. And so, again, there's a huge synergy there. And then another one in terms of the use of AI, if you look at how we develop new material systems today in the metallic space, it's kind of like you've got this big cauldron of molten metal. You've got the engineer, him or her, with a picture of the wizard hat with the stars and the moon, and they put in little pieces of different different metals, and then they make samples and they test them. And that's why it takes us sometimes decades to field some of these new material systems. And so what we're doing with AI and some of startups that we're partnered with is actually they use integrated computational material science. They use that to train an AI agent. They then make the coupons serially with robotics. Those same coupons are actually tested for hardness, for toughness, for fracture, for fatigue. And then that data go back in and retrain the AI, tune the models. And so this is actively being used today to discover new material systems. It turns out this is the way pharmaceuticals have started using AI probably about half a decade ago. And so we're actually lagging in this space. But the opportunities, what we're seeing already, are starting to see new material capabilities emerge that it just would have taken us phenomenally longer to get there. So now I'm going to talk a little bit more about propulsion systems. Now, I'll be careful of the audience here. I would normally say that a gas turbine engine is the most sophisticated mass-produced device known to humankind. I'm not sure that competes with a submarine. I'm not going to have that debate, but it's at least one of the top two. There's 40,000 parts in a large gas turbine engine. The parts are spinning at tens of thousands of RPM. In many cases, they're spinning literally within a hair's breadth of parts that are not moving. And the temperatures inside can be just incredible. If you think about what happens in a gas turbine engine, the air is compressed. As I compress air, it gets hot, like your bicycle pump. By the time I get to the back of the compressor, the air is hot enough to melt rocks. And then what do? We dump in fuel and we light it on fire. And then that air, that reacted mixture is expanded through a turbine, turns it into motion on a shaft, and the temperatures when you enter the turbine are hotter than the melting point of all the metals surrounding it. Don't think about that when you're flying home. So the point I want to make from this chart is that we make everything from the smallest, the center top, at the 12 o'clock is TJ150. It's our smallest engine. It's a 150-pound thrust engine. It's about this big. And you'll see more of that in a few minutes, all the way through very large gas turbine engines, both for military and for commercial. And the laws of physics and chemistry don't change whether I'm making it for a military system or a commercial system. So the things we learn in one domain can be optimized for a different domain. So I'll just sort of share a little bit more detail on that. On the top of these slides, you'll see the F-135 propulsion system on the F-35, and the bottom is that geared turbofan, the most advanced commercial engine. They all have the same piece parts. They're just arranged in different ways. They're just optimized for the mission. There are different constraints. They both have fans. They both have compressors. They both have diffusers and combustors inside. They both have mechanical components, bearing systems, lubrication systems. All of that is common. And of course, they both have turbines on the inside. And so with that, we optimize these for the mission. And so when you're flying low and slow, relatively speaking, you want to optimize for maximum efficiency. 30 to 40% of the cost of running an airline is fuel. About 30 to 40% of the cost of running a modern Air Force is also fuel. And so that becomes important for transport, for example. As you look to going fast and higher, there are other constraints. One of the major constraints is that we don't want to put big holes in the airplane for survivability reasons. And so having big fans like we have in commercial engines is not ideal for many of our military applications. So now I'm going to talk a little bit about digital and AI. And I'm going to use the jet engine as an example here because it turns out if you look back over the history of the company, over the last century, the second half of the last century, we introduced a new military engine about every decade. And what to set a historical context here, I'll talk about the computers we used and how fast they were to design and develop these. So the first one is the J57. It was actually a transformative engine, ended up on the B-52 and some other applications as well. We had computers in the 1950s at Pratt & Whitney. It was a job description. They were people. And they did one calculation every 10 seconds. It turns out it was mostly women because they did a better job. They used slide rules. And they did one calculation every 10 seconds. So we measure computers in terms of megaflop, millions of floating point operations or MIPS. And so that's 1 times 10 to the minus 7 computations, 1 times 10 to the minus 7 million instructions per second. In the 1960s, we designed the SR-71, as I mentioned, flies at Mach 3.5. We used a relatively simple computer, the IBM 704. The first fourth-generation fighters, the F-15, was introduced using IBM 360. I'll date myself. I learned on punch cards on an IBM 370. In 1990, we actually took a big step forward. We bought our first supercomputer. It was a Cray, and you can sort of see the speed of it here. And it cost us, so in 1986, we paid $34 million for that computer. That computer was not nearly as fast as this one is. So something to think about in terms of capabilities. As we went to the future, all the way to the F-135, we ended up taking all of the workstations on people's desks when they weren't using them, roped them together, and made our own supercomputers. And that really was what was used to develop the F-119 that went into the F-22. And now, really, we're doing all our calculations on the secure cloud. And so you are no longer limited in terms of the compute power. You're limited by the amount of secure cloud computing that you can purchase and you can afford on your contract. And so, again, a fundamental shift in the paradigm. Just want to also call attention to sort of how the data emerging from the engines on the other end of the spectrum in the fleet. We started with manual logs. We moved through literally mission data recorders that recorded a couple of data points, event recorders that so when something went wrong, you at least knew what happened. When we got to the F-119, we started with literally a CD loader. Think dashboard around the same time in your car. And today, under the appropriate secure conditions, we use mobile data gathering. Imagine from the commercial side, the airplane lands and everybody turns on their cell phone. Well, the engine and the airplane turn on their cell phones or its equivalent, and they call home and they fill up the data lake with thousands or tens of thousands of data points from that flight. On the military side, it's handled differently depending on which domain you're in, but it's a similar type of construct, and it's really changing the way we do fleet management and fleet logistics. And I'll talk a little bit in just a few moments about how that sort of connects now to the systems that we actually choose to engineer. And the way to do that is by connecting the model-based digital thread. So again, I could have used a military example here, but I just wanted to keep it completely clean. But it's the same. When we start by capturing the requirements are no longer stacks of paper like they used to be. They are now digital models. And those digital models plug into our engineering models that plug and play different technologies, put together the engines in the aircraft, fly the missions, or fly the city pairs, connected together to iterate and optimize so that the requirements and the technology selections are really the most appropriate for each other. When we come to the engineering piece, that's where the heavy lifting. This is where, when you start with those digital models, it lets you keep building those digital models. And it's really important, and this is an important message, you can't just look at a segment of the digital thread. You really need to connect it end to end. So those engineering models become the foundation for the rest of the life of the program. And in some military applications, that could be a century, almost a century. And so it's critical that we think this through and we build it with enough longevity and enough forethought in terms of access to the models, access to the data for in perpetuity in order to accomplish that. When it comes to manufacturing, we no longer just go cut chips. We model the manufacturing process. It turns out that we've been designing engines and airplanes. Nobody, and probably on the seaside as well, we can't make these structures. We can't deliver what we designed. And so the ability to model it and connect those two things is really another unlock that we haven't fully captured yet, but we need to. That really translates to having more capacity, and again, to counter some of our threats in Indo-PACOM. When it comes to the maintenance at the depot, we don't take apart the engine and look at all the pieces. Now, you take out the blades, you take out the parts, you take out the various pieces, it goes into a robot's hand, it gets imaged in stereo, and then that reaches back into the engineering model of the CAD file, and it locks it to the grid. So it snaps it to the grid of the CAD file, and then it reruns the actual models. We used to look at critical radii of curvature, or we used to look at the coating thicknesses. Now what we do is we measure all that stereographically, basically, and then it goes into the model, and then we rerun the aerodynamic model. So instead of looking at, say, 20 different critical dimensions on a part, you actually rerun the engineering model and say, can this deliver the function it needs? Not doing quality inspections or not doing depot maintenance on the basis of form and fit, but actually extending it to function. And that's something that we're starting to embrace. We've deployed some of this, for example, at some of the Air Force bases and at some of the depots, and it's really transforming the availability of parts to assure warfighter readiness of the components, the engines, and the systems. I'm going the wrong way, sorry. So really bringing it all together, the last piece is, and we don't do this very well today, is using all that fleet data and pulling it back into the design. Nobody's doing this effectively yet, but as these data become available, especially with application of AI, we need to figure out how to use it to stop designing things that just aren't going to be able to deliver. They're not going to be able to last under the conditions that they're being subject to in their application space. And again, I'll note, it's critically important that you bring together the entire model-based digital thread. It's not enough to do a piece of it. You need to start it and finish it and do it with that design in mind. I'll just keep going. Additive manufacturing, Admiral Small mentioned additive manufacturing. I'll say that additive manufacturing is a great opportunity. It's very, we do a lot of work in metal, different material systems, but metal is sort of the one that gives you significant capabilities in terms of warfighting in particular. It's easy to make a part that looks right, form and fit. Making the function is not as simple. Getting it right is really important, and it takes a number of things. Modeling the process, in situ measurements. I noted that the application, the first application that was noted this morning was a wire EDM process, I believe. It's actually a lot harder to get the qualities right when you use powder bed because of various factors associated with the powder bed process. So getting it right and being able to deploy that is really important. It's easy to make stuff. It's not easy to make good stuff. So that's a very important message. And the standards that you're all putting out there are critical. There are other groups doing standards for different design spaces. It's important that we get all these things right and get them harmonized. Now I'm going to show you an example. I mentioned the TJ150. This is the application I can talk about here is the MALD 9 that Raytheon makes. It's a 150-pound thrust engine. It lasts less than an hour and a half. Its red line is over 100,000 RPM. And it's got something on the order of over 100 parts. The touch time to make one is typically over 120 hours. And so somebody challenged me 6 or 7 years ago when I was at Pratt, can you print the whole engine? Well, this was the ideal case because it all fit in the build volume of the machine. And it turns out that we were able to do about a 98-to-1 part unitization. We've since taken that a lot further. We are now printing the entire engine. Maybe I'll go back because I talked too long. Maybe I'll go back. We're now printing the entire engine, and it optimizes out as 3 parts. So the inlet, the combustor, nozzle, and exhaust system, and the rotating components, and you'll see that in just a minute. The turbine, the compressor, and the shaft are printed as a single piece. And so not only can you print these en masse, but in principle, you can, as long as you're discretized on the bearing sizes, there's the 3 pieces here. And they just come together. As long as you discretize on the bearing side, you can actually, to some degree, scale the thrust. And so imagine a mass customizable, affordable mass. I'm using mass 2 different ways in that sentence, as an opportunity for the future. So we're starting to use this. It's being applied in a number of applications, and we've flown some of these earlier this year. Now, I'm going to talk about another application, and this is an interesting example of a technology unlock. Remember I said our industrial base is constrained. Well, you think about a propulsion system, and you've got in there liquid fuel propulsion system. You've got in there these blades, airfoils, compressor blades, turbine blades, fan blades. These are exotic materials that are hanging out there in the flow path, and they need to survive, and I need to manufacture a lot of these because there's a lot of these in every propulsion system. Imagine if I can do a rotating detonation engine where instead of having the parts move, I get a detonation wave that moves and does the compression for me. And so we've been developing this, and we've recently demonstrated that we are making thrust, and this is capable of propelling a projectile up to a couple, not quite hypersonic, but well above Mach 1. And so just a little bit about how this works. And so the simplicity here is just so profound. It's really just a pipe in a pipe. The dimensions are kind of important. The shape of things is kind of important. But it's just a pipe in a pipe. And what you do is you put the liquid fuel in. And you can make these with solid propellants as well. And there's some distinctions with those. But there's fuel and air passages. The fuel is introduced through nozzles and the outer of the circumference. The air is introduced through the core of the device, and then it's allowed to mix. Here comes the air. And then you essentially ignite it, and just due to the natural acoustic frequencies under the exact right conditions, you get this thing going, and it starts to form essentially a detonation wave. You're not actually burning the fuel-air mixture, you're detonating it. And so it's actually a much more efficient, significant increases in range for that projectile. And you can make an awful lot of these. We're really excited about the progress on this, and we're looking for an opportunity to go fly one. A little more on digital. Pratt & Whitney has a program of record for the sixth generation propulsion system. This is the adaptive propulsion system that is being developed. Earlier this year, we completed our CDR, and for the very first time with the customer in the room for a week or so, there was not a single PowerPoint chart used. There was not a single document produced. Everything was digital. Everything lived in the single source of truth. And that single source of truth was in the system. Any questions that were asked were actually done from interrogated into the database directly and real time by the engineers. We're now building this engine, and we're on track to run this engine the next couple of years. It will be part of the down select for future 6th-gen platforms for the services. I just want to say a little bit about modeling and simulation in terms of, there's a number of tools that we all use across the industry and at DoD. We start sort of at the physical system. We build up to the battle space, eventually look at sort of the, what does a particular mission do? But ultimately, we need to look at the full theater. And there's a number of certified tools that we use in concert with the department. And we've developed our own internal tool. We call it Arcade, which allows us to very rapidly simulate the theater engagements. And so this is showing an engagement, red versus blue, for a particular length of period of time with an over-the-top incursion. It was fast enough we could run the red versus blue Monte Carlo simulations, run hundreds of simulations. What we've now been doing is going back into the physical system. So let me give you an example. I was looking at a technology insertion in a particular asset that was part of a strike package in Indo-PACOM engagement, and we were able to run the mission and just sort of cycle it to see what the change in the outcome was by any given discrete technology that I might just choose to insert in one of the particular effectors or one of the particular subsystems. And so the ability to rapidly look at this, and then more recently, we've put on top an AI layer, and so that can now sort of look at the optimums, essentially what the choices that are made through the simulation. Again, it speeds it up because you don't have to run nearly as many Monte Carlo simulations to get to answers. So this is it's one of these things. Operational analysis can be done relatively easy. Doing it right and getting enough fidelity in there, and using the right systems underneath so that you trust the answers is a critical thing. But we're now getting to a point where we can now sort of reach back into the model-based digital thread, use that single source of truth in the model-based digital thread to understand how to differentiate ourselves in particular engagements. And that will be extremely powerful as we look to the future. Last thing I want to say is we have 85 university partnerships across RTX. And the message I have for all of the science, engineering, mathematics, technology students out there, the STEM students, and to all of you, that aerospace is cool again. We've got the new space economy. We've got defending our freedom. And we've got, at least parts of the world, the emphasis on sustainable aviation. And so we lost from our industry probably about 15 to 20 years worth of really good talent to tech. And we're starting to get them back. We're starting to inspire them. And it's important that we share this message to all those that will listen. So with that, I'll stop. And I think we have a few minutes for questions. Are there any questions?